So number 11 says a point is selected at random from the disk R equals xy in R2, x squared plus y squared is less than or equal to 1. Let x be the x coordinate and y be the y coordinate of the point selected. Determine if x and y are independent random variables. So first we want to find our joint probability density function of x and y. And when we're given a disk, that's simply just 1 over the area. And here, with a radius of 1, our area is pi. Next, we can find our x and y bounds by simply manipulating the function that it gives us, x squared plus y squared is less than or equal to 1. Now, to determine if they're independent random variables, we need to find the marginal function of both x and y. So first, we'll start with the marginal function of x, which we're going to integrate over the bounds of y, which are given by negative square root 1 minus x squared to the positive square root of 1 minus x squared. And our integrand is going to be the joint PDF, which is just 1 over pi. And we're integrating all the y's out, so this will be dy. And after deriving that, we're going to get a final answer of 2 over pi times square root of 1 minus x squared. And now we're going to do the same process for the marginal of the y function, which we're going to use the x bounds, which are negative square root 1 minus y squared to positive square root 1 minus y squared. The integrand is going to be the same as before with 1 over pi. And here we're integrating all the x's out, so it's going to be dx. After integrating, this will give us a final answer of 2 over pi times the square root of 1 minus y squared. Now to check if they're independent, we need to see if the marginal of x times marginal of y equals joint probability density function. And as we can see, after multiplying these two together, that does not equal 1 over pi, therefore x and y are not independent. Next is number 12, which says a point selected at random and uniformly from the region R equals xy, where the absolute value of x plus the absolute value of y is less than or equal to 1. Find the conditional probability density function of x given y equals y. So to solve this problem, we're going to need to find the joint probability density function as well as the marginal function for y. So for the joint PDF, this is just going to be 0.5 for all absolute value of x plus absolute value of y is less than or equal to 1, and it'll be 0 otherwise. And it's going to be 0.5 because the maximum value for this function you can have is 1, and the minimum would be 0, and it's uniformly distributed, so this will make the joint PDF 0.5. Now for the marginal of y, using the property of symmetry, you can put the 2 out front, since this problem deals with absolute value, and then you're going to integrate for all x, and your x bounds using the function that it gives you are going to range from 0 to 1 minus the absolute value of y. Your integrand is just going to be your joint PDF, which is 0.5, and you're integrating for x, so this is going to be dx. And after integrating, this gives you your marginal y to be 1 minus the absolute value of y. Now, for the conditional probability density function of x, we need to divide the joint probability density function by the marginal for y. And we've solved for both of these, so this is just going to be 0.5 over 1 minus the absolute value for y, which simplifies to 1 over 2 times 1 minus the absolute value of y. And the bounds for this, x is bounded by negative 1 plus the absolute value of y on the lower end, and then its upper bound will be 1 minus the absolute value of y. And then y is simply just bounded between negative 1 and 1. Next is number 13, which says a lost tourist arrives at a point with 3 roads. The first road brings him back to the same point after 1 hour of walk. The second road brings him back to the same point after 6 hours of travel. The last road leads to the city after 2 hours of walk. There are no signs on the roads. Assuming that the tourist chooses a road equally likely at all times, what is the mean time until the tourist arrives to the city? So first we're going to want to find our variables, where t equals the time to reach the city, R1 equals the event that road 1 is chosen, R2 equals the event that road 2 is chosen, R3 equals the event that road 3 is chosen. Now the question's asking us to find the expected value for t, which we can use using conditional expectation, where E of t equals the expected value of the time given that you choose road 1 times the probability that you choose road 1, plus the expected value of t given that you choose road 2 times the probability of choosing road 2, plus the expected value of t given that you choose road 3 times the probability of road 3. Now we can simplify this, as we know that the probability of road 1 equals probability of choosing road 2 and road 3, which is just going to be 1/3, so we can factor out a 1/3. So now it's just the expected value of t equals 1/3 times the expected value of t given R1 plus the expected value of t given r2 plus the expected value of t given r3. Now we need to find each of these conditional expected values, and your expected time given that you choose road 1 is just going to be 1 plus the expected value for t, because after 1 hour you return right back to where you started, and this problem is assuming that when you come back you still have no idea which road is which. And it's going to be the same thing for road 2, except it's going to be 6 plus the expected value of t, because you're walking 6 hours, and then again you're back to ground zero. And then for road 3, the expected value of t, given that you choose road 3, is just going to be 2, because no matter what, if you choose the third road, you're just going to make it to the city in 2 hours. Now, after plugging all of these in, you get expected value of t equals 1/3 times 1 plus the expected value of t plus 6 plus the expected value of t plus 2. After some simple algebra, we get that the expected value of t equals 9 hours. Next is problem 14, which states x, y, and z are jointly defined random variables. And for part A, it says show that the expected value of x equals the expected value for the expected value of x conditioned on y. First, it's important to note that the expected value of x conditioned on y is a function of y. Since this is a function of y, we're going to integrate over all y values with the expected value of x conditioned on y multiplied by the marginal of y, dy. Since we know the equation for the expected value of x conditioned on y, we can simply just plug this in to the whole formula, giving us the integrand for all y's times the integrand of all x's with x times the marginal for x conditioned on y, dx, and then this is multiplied by the marginal for y, dy. Sorry, I made a slight mistake there, but next we're going to want to use the principle that all integrals are finite, and we can now rearrange this to start with integrating for x, with x times integrating for all y, for the marginal x conditioned on y times marginal of y, dy, and then dx on the outside. And then what we have in the parentheses simplifies to the joint PDF being integrated for all y's, which is also the same thing as the marginal for x. So now this gives us a very simplified version of it being integrated over x values with x times marginal for x dx, and we know that this is just the equation for the expected value of x, therefore proving that the expected value of the expected value of x conditioned on y is simply just the expected value of x. Now for part B, it said show that the expected value of y conditioned on z is equal to the expected value of the expected value of y conditioned on x and z conditioned on z. Now to start this messy formula, we're going to use our laws of conditional expectation to get the integral for all x's times the integral for all y's with y times marginal of y conditioned on x and z, dy times marginal of x conditioned on z dx. Now again, we're going to use the principle that all integrals are finite, and we're going to rearrange that to be integrating for all y's with y times integrating for all x, with the marginal of y conditioned on x and z times marginal of x conditioned on z dx, all being integrated dy. We can then further simplify what's in the parentheses, so it now becomes integrating for all y's with y times integrating for all x with the marginal of y and x conditioned on z dx times dy. This again simplifies to make the overall equation integrating for all y's with y times the marginal for y conditioned on z dy, and we know that this is simply just the formula for the expected value of y conditioned on z, and then this now proves that the expected value of the expected value of y conditioned on x and z conditioned on z is equal to the expected value of y conditioned on z.